All righty then. So I'm going to go back to this, this. All right. He'll get a B. He's going to fail. A, B. She'll get a C. I have confidence in her getting a C. A, probably an A. C. Probably a B. I'll blow the final. She'll blow that. B. I'll have to see if she pulls it out. All righty then. Oh. This is why I wear a hat. This is why I wear a hat. think so. Hi, Kevin. Hi, Kevin.
Hi.
Now I got my ears on. Hi, Kevin.
Hi, how you doing?
I'm doing fine. Anything I can do for you?
Not really. I just wanted to make sure I got on this time. I missed it like 1 or 2 times ago, so I was trying to get on early.
No problem. Uh, no, it's no problem. So I'm just gonna wait for about 14 minutes to begin then, all right?
Sounds good.
All right. If there's nothing I can help you with?
I don't think so, except for maybe about like the final. Is the final cumulative for everything?
Yes.
And then is there like a study guide or a practice test for the final as
The
well?
study guide or the practice guide for the final are the 4 tests I've already given.
Sounds good. Okay.
That plus the practice tests that are out there, all right?
Awesome.
Maria, can I do anything for you?
No, I was just coming in.
No
like
problem. No problem. That's basically what I'm doing in here. So I'm not going to start for another 15 minutes unless somebody has questions.
Is today's class a review?
No,
No?
no. We have uh, we have uh, some things about quantum mechanics we have to get through today. It's
Okay.
not really memorization, but it is some things I got to teach you, and you're going to be able to use them to be able to predict other things that happen.
Okay. So before the exam, will we have a class like to review or?
Nope,
Okay.
nope. I'm sorry. You have to review. You have the 4 tests I've given you previously,
Okay.
and you have the 4 practice tests.
All right. Thank you.
Hey, Winifred, how you doing?
Hey, what's up?
Not too much. You have anything to ask me?
Not. No, I do not.
Okay. No
So I
problem.
don't.
No problem. I just have one email I have to write. And hi, Kelsey.
Hello.
Any questions? I'll be there in a second. I've got only about a handful of you in anyway. And believe me, you guys need this. I'm finishing up a email and I will be right with you. You people. Okay, looks like I got 9 of you in here. Hi, Richard. How's it going?
What's up, Mr. P?
It's going to be an interesting day.
Oh,
I only got 9 people in here, and this is definitely going to be very prominent on the last test. This is the last class we have before the 4th test. There is no review. Okay. While I have the time, I'd hope to have a little more people in here than this, but while I have the time, I wanted to take this moment to thank you all. It has been my honor for teaching you the entire semester, and it's been great. I've always looked forward to my 12 o'clock arrival time into this class, and I've appreciated your working with me this semester. It's been a good class.
Thank you, Mr. Professor.
Thank you, Noah.
Popovich.
Thank you very much, Noah.
I'm gonna cry, Mr. P.
Yeah, well, I can tell that your emotions just aren't overcoming you yet, Richard. Anything anybody needs to talk about from Monday's lecture?
Nah, not really.
I just went through, Noah, was it you I went through or Ian? It must have been Ian. I managed to get through a lot of Lewis dot structures with Ian during the lab portion today. Nobody has any questions about Lewis dot structures, Vesper? The test will cover gas laws, Lewis dot structures. It will cover Vesper and quantum mechanics. There are, I want to say, roughly about 25 questions, probably about 5 problems, mostly gas laws, but there are some quantum mechanic problems. And the rest are going to be multiple choice based upon Vesper, gas laws. There's going to be Vesper gas laws, Lewis dot structures, and what I'm going through today. Any questions on that?
No,
How
sir.
many were the written ones? Let's show your work once again. How many questions? Are those?
Probably about 5. And yes, absolutely. If you do not show your work on this test, you will not get any credit. Show me at least the setup of the problem. You don't have to show me each and every step, but I need to see at least the setup for the problem. The more work you show me, the better off you will be. Okay. Final. All multiple choice, true, false. Which is a good thing and a bad thing, because if you get the right answer, you're good. If you don't, then it's an all or nothing proposition. That's why multiple choice tests are not the best. But I have a quick turnaround time. I literally have to get your grades in the day of. So homework assignments have to be in by, I believe I stated the 8th of May. All homework. Remember, you're still allowed to turn in homework. You're still allowed to turn in homework. The second pop quiz. Make sure you answer all the questions. You do not have to really answer them, but if you don't want to answer them, I need you to say, I do not choose to answer this question. Nothing really, all it's about is in regard to the course. I'm going, literally speaking, after I grade your finals, the next day I'm headed off to Savannah for 5 days. I will not see those results until at least May 17th or so. Any questions? I will, participation grades and homework grades will be in at least by the 8th of May. Any questions?
Sounds like you got your work cut out for you, Mr. P.
I always do at the end of every semester. All right, guys. I want to hear an we're going to do a little meditation.
Woosah.
Now, we're following the mantra of Mr. P. Listen to me today, because this stuff is not that hard. If you follow the rules, the stuff I'm doing today is not that hard. Are we good with that?
Mhm.
Yes.
Okay, now I got to find the PowerPoint.
What are we going over today?
Okay, show all windows. We are going over the second part of quantum mechanics. I got to go find the video again. Sorry, I somehow lost the, there we.
Yeah, we haven't had many videos. I noticed.
Not the, yeah, you're right. Okay. I don't want to do this. I want to do something else first. That's not what I want to do. There we go. That, I think, is what I want to do. Okay, ladies and gentlemen, especially, I want to point something out. This has been here the entire semester. I don't think you guys knew it was here. I mentioned it on the first day. Let's go into the course. We're going to go into quantum mechanics, test 4, quantum mechanics. If you go into that, there is something called the online outline. Click on it. You will pull up a page that has videos. If you are having trouble with a particular subject matter, like what we're going through today, look in the online outline. There will be a video, several videos, okay? If you're having trouble after we speak today, first of all, give me a call. I'll be happy to answer anything. Second of all, look at the videos. Sometimes you can get a different perspective from looking at the videos than I'm giving you, and that other perspective something may click for you. So that's where you get the videos. All right, now we're going to get back into what we really need to be doing. Everybody seeing the slideshow?
Yes.
Yes.
What?
Not anymore.
I know. That's because I did something stupid. Slideshow from beginning. That's what I want. Why is this not paying? Thank you. Okay. The first couple slides here are slides you've seen before. Stuff that was doing the bonding. This is when I was using one PowerPoint rather than two. Now remember, Planck came up with the idea of quanta, that when we're dealing with the microscopic world, we're dealing with little packets of energy to go from one energy level to another. And as a matter of trying to explain things, Max Planck came up with what he called the solar system atom, which meant that the electrons were orbiting in specific orbitals around the nucleus, and that each one of these orbitals had a specific energy. And to go from one orbital to the next, you had to use that specific amount of energy. If you used a different kind of energy, you couldn't go from one level to the next. So, Bohr was wrong. Have I explained Schrodinger's cat to you, ladies and gentlemen?
You touched on it last class, but I think you
All right.
did.
Schrodinger was a chemist in the early 20th century, and he eventually came up with what we're going to be describing later on today. And basically, the analogy he came up with for saying, all right, you cannot apply macroscopic measurements to microscopic systems. You can't take a ruler and measure exactly how far out from a nucleus an electron is. You can't do it. The analogy he came up with is you put a time bomb around a cat. You shove it into a box and you seal the box off. The time bomb has a 50-50 chance of going off. Is the cat alive or is it dead?
Neither.
Exactly. You don't know. The only way you have of knowing is opening the box. And by opening the box, you have changed the system. You no longer have a sealed box. Your box is now open. So you cannot apply macroscopic measurements to microscopic systems. This is first espoused by Walter Heisenberg. And what Heisenberg's uncertainty principle, has anybody ever heard of Heisenberg's uncertainty principle?
Yeah, I think it was a really good TV show about it.
There was Breaking Bad. Breaking Bad, the guy's name, he called himself Heisenberg. That may be what you're referring to.
I think so too.
Okay, Heisenberg came up with the proposition that you can't know the momentum of a particle and its location at the same time. Because whatever you do, if you use light to figure out where that particle is, the light hits the particle and moves its momentum. Okay, if you try and figure out what this particle's momentum is, you've changed its position. You cannot determine the position of a wave particle and its momentum at the same time. What you can do is you can limit where the electron can be into a little box. And you can apply an infinite number of momentums to that. But still, you have uncertainty because you have that little box. Okay? You can exactly know where the position is, but the momentums are going to have a little box about them. So basically, what Erwin Schrödinger did was he applied energy to something called a Hamiltonian operator, which you guys don't need to know anything about. All you need to know is it's a mathematical proposition. He applied energy to this Hamiltonian operator and came up with a formula, which is H psi is equal to E psi, where psi is what is called the wave function. Basically, what he's doing is he's applying he's applying momentum and position here and creating those little boxes. Now, if you square psi, that becomes the probability of the electron being in that location. You can't tell where the electron is. All you can tell is the probability of where it is. So orbitals do not have sharp boundaries. Noah, that electron from that molecule of carbon dioxide that you just exhaled, it's possible that that electron is right next to me right now. That possibility exists. All Schrödinger did was he applied a mathematical probability to where the electron could possibly be. And we've defined an orbital size as the space that contains 90% of that probability. Now, we depict them, an s orbital, we depict as being a sphere, but it's not really like that. It's more like what we see in A. If you notice, the center of that sphere in A is really, really dark. And as you get further and further out, you get less and less color, less and less purple color. This indicates as you get further and further away from the dead center, you have less and less probability that that electron is there. Now, we need to describe the orbitals. Orbitals are the energy levels of the electron. It's dictated by the primary quantum number, which is n. And the primary quantum number can have a value. According to the periodic table that we have right now, it can have a value from 1 to 7. So the bigger the number, the further out from the nucleus that orbital is, and the more energy it takes to keep that electron attracted to the nucleus. The lower the number, guys, let's face it, it's the lowest denominator. If you had a choice between shoveling dirt for an afternoon or sitting on your couch, you're going to go for the sitting on the couch because you don't have to do as much work. Electrons fill the lowest energy levels first. And when Schrodinger did his calculation, he determined that each shell, each energy level has different types of sublevels. We can have S sublevels, and S sublevels geometrically look like spheres. We can have P sublevels. They geometrically look like a balloon that is squeezed to nothingness in the center, or a dumbbell if you want. P orbitals are located directly along the X, Y, and Z axis. Now, each sublevel can hold 2 electrons. S has only one type, so S orbitals can hold only 2 electrons since they only have one sublevel. P, on the other hand, can hold 6 because we have 3 sublevels. Each one of them can hold 2 electrons. We have another type of sublevel. These are called the d orbitals. And this is like if you take a balloon and squeeze it in 2 different places. So you get 4 different lobes out of them. First lobe is located on the YZ plane. Another one's located on the XZ plane. One is located on the XY plane. One is located on the axes of the XY. Then we have this funky looking one over here that looks like a big dumbbell with a ring going around it. Notice 5 sublevels. Each sublevel can hold 2 electrons. So the Z sublevel total can hold how many electrons?
Is it 6?
How many sublevels does Z
10.
have?
Can it hold 10?
It can hold 10. There are 5 sublevels. Each sublevel can hold 2. So Z can hold 10. There is one. Go ahead.
Where are the sublevels?
They are within each energy level. And I will get to that in a second. Okay? I will explain that, where they are and how they come to be in a second. There's one more type of sublevel, and that is the F. F has 7 different sublevels. Each one of those can hold 2. So if there are 7 sublevels, each one can hold 2. How many total electrons can F orbitals hold?
14.
14. Again, this is not magical stuff. This is basically kind of fairly easy. So now I have to designate not only what energy level the electrons are in, but what sublevel that electron is in. So I have to designate it by whatever energy level it's in, whichever its primary quantum number is. That goes first. The second thing is the type of sublevel, which indicates the shape of the suborbital. Remember, again, these things are nothing more than a representation of a geometric representation of the probability that an electron is there 90% of the time. The letter designation gets followed by the number of electrons in that type of suborbital. Questions so far? So shells, the orbital defines the size. The energy level defines the size of the orbital. The only difference between 2s and 3s is the fact that 3s is larger than 2s. The only difference between 3p and 4p is larger than 3p. The only difference between 5z and 4z is smaller than 5z. The orbitals, those letter designations define the shape of the probability pattern. For our purposes, we're going to designate that with the letter. And the suborbitals are also defined by another quantum number, which indicates which one of those suborbitals the electron goes into. So we're going to be defining, when we do something called electron configuration, we're going to be defining. The first number is going to tell you the energy level. The letter is going to tell you the shape. P means a 2-lobed orbital in the X, Y, or Z subscript on the p orbital tells you which particular suborbital the electron is in. Now, remember I said we load the electrons from the lowest energy level to the highest. Because S only has one suborbital, there are no degenerative orbitals. It just exists as the one orbital. P has 3 orbitals, 3 suborbitals. Each one of them has the same amount of energy. So literally speaking, if I'm putting an electron into the P's for the first time, it can go into any one of those 3 orbitals. If I am looking at a periodic table, the s orbitals are designated by the first 2 columns of the periodic table. The alkalines and the alkaline earths are where the s orbitals go in. The p orbitals are the last 6 columns, the columns totally to the right, with the exception of helium. Helium is only there because it's a noble gas. Helium is an S, so it should rightfully be over here, but it is a noble gas, so that's why it's set over there. P's are in the last 6 columns to the right. The D electrons are in this trough. They are the electrons that go between the S and the P. Now, if we were to put the F's in their rightful place, we would either end up having a piece of paper that is 3 times as long as we want it to be, or we would have to fold it over. Rightfully, the F's start here, and just like the D's made a trough, the F's would make a trough down below the S and the D's. And you would have 14 spaces that go in right here, then we would proceed with the D's. But if you want to designate them in the periodic table, they are generally placed as 2 rows in the bottom of the periodic table. Any questions so far?
I don't think so.
Okay. Now, when we go to fill these, we have to realize that the suborbitals can hold a maximum of 2 electrons, but if they're holding 2 electrons, they cannot have the same spin. One spin has to be clockwise, the other one has to be counterclockwise. No suborbital can have more than 2 electrons, and when there are 2 electrons in a suborbital, one spin has to be clockwise, the other has to be counterclockwise. Now, when we physically designate this, in order to designate an electron with a clockwise spin, we designate that with an arrow going up. An electron with a counterclockwise spin, we designate that with an electron going down. So, a little bit of review here. The s orbital, no degenerative orbitals. It has one suborbital. Each suborbital can hold 2 electrons, so the s sublevel can hold 2 electrons. The p suborbital, the p sublevel has 3 suborbitals. Each suborbital can have 2 electrons, so the p sublevel can have 6 electrons. D sublevel, 5 suborbitals, each one can hold 2 electrons, so the D sublevel can have a maximum of 10 electrons. F, 7 suborbitals, each one having 2 electrons. The F level can have a maximum of 14 electrons. Have I got you with me so far?
Yes.
Okay. As a general rule, you remember I told you that they fill from the lowest energy level up? There are exceptions to this. The 3D sublevel fills after the 4s. This is because the 2 sublevels have about the same energy. And you get extra energetic stability having a full suborbital or having a half-filled suborbital. So literally speaking, if this is the 4s and this is the 3d, by putting 1 electron in the 4s, I have half filled it. That lowers its energy level a little more than the 3d. So 4s's get filled before the 3D. Similarly, 4Fs, the 6S gets filled before the 4F. The 4F gets filled before the 5D. Now, you may just be going like, sorry, you may just crumple up your piece of paper and just throw it away at this point. There's an easy way to figure out which levels get filled first. All you have to do is make this chart. You're going to put 1S on the bottom. Next level up, you're going to put 2S, 2P. Next level up, 3S, 3P, 3D. Next level up, 4S, 4P, 4D, 4F, and so on and so forth. Now, you are going to draw diagonal arrows through these number letter designations. You're going to go the tail of the arrow to the head. You're going to go through 1S. 1S gets filled first. You're going to draw another arrow through the 2S. So we go from the head of the first arrow to the tail of the second arrow. Go through the head, 2S gets filled next. Go from the head of the second arrow to the tail of the third arrow. 2P gets filled, then 3S. Again, head of the arrow down to the tail of the fourth arrow, fills 3P, 4S. Now, there is the first anomaly. We're not filling them in order after this. So, from the tail of the fourth arrow to the head, we filled the 3P, then the 4S, then we go back to the tail of the fifth arrow, 3D, 4P, 5S, back to the head of the 6th, 4D, 5P, 6S, back, 4F, 5D, 6P, 7S. Are we good? Do we understand? This is the order at which the sublevels fill. Do we understand that all you have to do is make this little graph here? Draw the arrows, and that will tell you which one fills next. Or you could memorize it. Questions on this?
I don't have any questions.
So we are going to start with an electron configuration. We need to tell which energy level it's on, what the sublevel letter designation is, and how many electrons are in that sublevel. We fill bottom ones first, and each subsequent level fills up. So if we're going to deal with sodium, how many total electrons does sodium have?
Sodium has 1, right?
Nope, it has one valence electron. Total number of electrons.
Not sure.
Nobody has a periodic chart open. Grab your periodic charts. You need them to understand this.
11.
11. So I got to account for where those 11 electrons are. First one goes in the 1s. One sublevel, 2 electrons. So I designate those first 2 electrons to go in 1s2. Head of the arrow down to the tail. 2s is filled next. Again, S, one sublevel can hold 2 electrons. So far I have 1s with 2 electrons in it, comma, 2s with 2 electrons in it. I go down to my tail. From 2s down to the tail, I fill the 2p next. 2p has 3 degenerative sublevels, so each one of them can hold 2 electrons. So my next level to fill is the 2p6. Now, if I've counted my electrons so far, the 1s, I put 2 electrons in. The 2s, I have put 2 electrons in. 2 plus 2, that's 4. In the 2p, I've just added 6 more electrons. So 4 plus 6 is 10. For sodium, how many electrons do I have to fill into a suborbital?
11.
I had 11. I've just designated where 10 of them go. How many more do I have to designate? How many more are left?
1. And you can put it in the 3s. So it'd be 3s1.
So the total electron configuration for sodium is going to be 1s2, 2s2, 2p6, 3s1. Questions? Questions, ladies and gentlemen? This is a pattern. This pattern is going to repeat. If I choose gold to do an electron configuration, the first 10 electrons for gold are going to be 1s2, 2s2, 2p6, and then I'm going to go on from there. This pattern is going to continue throughout the periodic table. Is this making sense, ladies and gentlemen?
Yeah, I think so.
So if I'm going to do cobalt, I look at my periodic table. Cobalt has 27 electrons. Noah?
Yes. Sorry, I was trying to unmute my microphone.
Cobalt has 27 electrons.
Right.
Where do the first 2 go? Look at the chart. Look at the graph I have on the screen now.
Okay.
And remember,
Is it the 1s?
It's first 2 electrons go in the 1s. They are designated as 1s2, comma.
1s.
Now, Noah, where do the next 2 go in?
2s.
And it's designated 2s superscript 2, comma. Noah, the next electrons, where do they go in?
2p.
How many electrons go in the p?
I think it was 6, right?
Good. Winifred, after the 2p, where do the next electrons go?
3s.
3s. How many electrons can an s hold?
2.
2. So that gets designated as 3s2. Winifred, after the 3s, where do the next electrons go?
3p.
How many electrons go in there?
6.
Okay. Michael. Now the funky one. After the 3p, where do the next electrons go?
4s.
4s. Now, if I count the number of electrons I have designated so far, 1s2, 2s2, that makes 4 total. 2p6, that makes 10 total. Add another 2 from the 3s, that's 12. 3p designates 18. The 4s, another 2, I have designated where 20 of those electrons go. Cobalt has 27. How many more electrons do I have?
You have 7 more electrons.
7 more. Now, who answered that? Michael?
Yes, sir.
Where are the next electrons going?
They're going to go into that 3D orbital. Which can
How
hold-
many electrons can the 3D accommodate?
Is it 10?
10. So, do I have more than 10?
No, you have 2 less, or you have 3 less than 10.
So, I am going to designate those electrons that go into the 3D as 3D7. Is this making sense, ladies and gentlemen? Come on, talk to me.
Yes.
If you are totally
Yes, sorry,
out in
my
left
thing was-
field, if you're totally lost on this, ladies and gentlemen, you are not going to do well on the test. I need you to tell me if this is not making any sense to you.
I think it's making some sense.
All right. We're going to call on more people. Argon. If you look at argon, argon has 18 electrons. So, Richard, have I called on you yet about this?
Nah,
Richard, where do my first 2 electrons go for argon?
1s.
1s, how many go in there?
2.
So, if I had started with 18, I subtract 2, I got 16 left. I got to designate.
Yeah,
Where do the next ones go, Richard?
they go 2s.
Again, S can hold how many electrons?
2.
I subtract 2 from 16. I got 14 now I have to designate.
Yeah.
Let's see who else I need to talk to about. Kevin,
Yes, sir.
we are doing with argon. We've so far gotten 4 electrons, 2 going into 1s, 2 going into 2s. What is the next orbital that electrons go in?
2p,
How many can the 2p hold?
6,
So that's 2p6. We had 14 left. I subtract 6 away. That gives me 8. Kevin, where do the next electrons go?
3s,
How many can the s hold?
2,
So I subtract 2 from the 8. I have 6 left. Angelica,
Yes.
where I've designated everything through the 3s. Where do the next
3p6.
electrons go?
3p6.
Can P hold 6 electrons?
Yes.
So they're just going to go there. So my total electron configuration for argon is 1s superscript 2, comma, 2s superscript 2, comma, 2p superscript 6, comma, 3s superscript 2, comma, 3p superscript 6. Are we getting the hang of this, guys?
Yes.
All right, now let's look all the way down to lead. Oh dear God. I'm going to have something that has to go into the 6p level. Look at that. For God's sake,
82.
I got to do all of these.
Your professor's actually kind of.
What's that?
It's 82.
It's 82, yes. But I got to go through all of these suborbitals. What a pain in the ass. Right? Isn't that a pain?
That's a pain.
Yeah.
So there is something called an abbreviated electron configuration. Now, have you noticed that all the patterns we have done to this point, they're all the same, right?
Yes.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. It's all the same, correct, ladies and gentlemen?
Yeah.
Yeah.
So look at your periodic table. If I am dealing with the electron configuration for iron, isn't the electron configuration for iron and argon going to be the same up to the point of argon? They're only going to differ after argon, right?
Yeah.
So what if I put argon in parentheses, and that's going to designate that the electron configuration to that point mimics argon's. I then look, the next one I have to fill after argon's 3p6 would be the 4s2. So I put brackets, argon, I continue on, 4s2. The next one that gets filled is the 3d. I count over 1, 2, 3, 4, 5, 6. There are 6 d electrons for iron, so they get designated as 3d6. Doesn't that make your life a whole lot easier?
Yeah.
If I'm dealing with lead, okay, what we're looking for is we are looking for the noble gas that directly precedes lead in atomic number. Lead is 82. I can't use radon, which is 86, because that has too many electrons in it. But I can use xenon, which is 54. So if I'm going to do an abbreviated electron configuration of lead, I'm going to put bracket XE in bracket. Then I'm going to go to where cesium is. There are 2s electrons there. So I've got xenon in brackets, 6s2. Then, if you notice, from the 6s, it goes down to the 4f. I count 14 electrons in the F level. So I designate that as 4f14. After the F level, I go to 5d according to my arrows. I can hold 10 electrons in the 5d. So I'm all the way, guys, right now to mercury. After the 5d comes a 6p. I count 2 boxes over there. So therefore, the last electrons go in the 6p superscript 2. So the abbreviated configuration for lead is going to be XE brackets 6s2, 4f14, 5d10, 6p2. Do we understand the concept of the abbreviated electron configuration? I'm hearing crickets, guys.
Yeah.
You
Could
guys
you-
are getting this a lot easier than my SPC. Either that or I'm teaching it a hell of a lot better.
Could you
If-
do it with,
Go ahead.
sorry, could
Go
you
ahead,
do it
Maria.
with lead?
Could I do what with lead?
Like the,
The full one?
no, the short one again?
Okay, I'll do both. Okay,
Okay.
and show. And I am going to go home. I need to get this away from here. Home. New slide. Okay, we're going to do layout, title and content. Okay, follow with me. 1s2, comma, 2s2, comma, 2p6, comma, 3s2, comma, 3p6, comma. This is where it changes, 4s2, comma, 3d10, comma, 4p6, comma, 5s2, comma, 4d10, comma, 5p6. Now, if you've been following along with me on the periodic, oops. Yes, if you've been following along with me on the periodic table, or if you counted the number of electrons in there are 54 electrons. Right now, this is equal to, do you all understand that? If I was going to do the electron configuration of xenon, it would be the same thing as this.
Yeah, I understand that.
So going on from there for lead, my next orbital, 6s2, comma, 4f14, comma, up to 5d10, comma, 6p2. Understand that this part wouldn't normally be in the full electron configuration. If I want to do the abbreviated, you saw what a pain that is, right, guys? If I want to do the abbreviated one, all I have to do is type in XE bracket. XE brackets encompasses all this electron configuration. Now to get the rest of it, I just have to do from xenon forward. Questions? Okay, now I'm going to do something else to you. I'm going to do something else to you. New slide. Let's go 4p6. Which element is it?
Would that happen to be rubidium?
You're good.
Whoa, explain how you found that.
Like that. Did you see, guys, how quickly he did that?
It was quick.
Now, you can do the same thing. All you have to realize is that this is where each one of the suborbitals exists. 1s is going to be here and here, 2s, 2p, 3s, 3p, and so on and so forth. So all you got to do, even though I listed all this extra information, it's crap. It's going to be the same thing. From here down is going to be the same thing. This last one is the one that designates where the element is. So we know it's in the 5th level, we know it's S, and we know there's 1 electron in there. So we're going to look at our periodic table. This is the 5s. This is the first box. So all you got to do is count 5 levels down, 1 in, and it is rubidium. Questions on that?
No, that kind of cleared it up.
Where's it at? Where did I put that? I don't even know where the hell I'm at right now. Oh, there it is. Okay. Which element is it? Extra credit. Which element is it?
Is it endymium? I don't know how to pronounce it.
Techni.
No, it's not that.
That
Who
looks
got
like
the first
Indium?
one?
Indium is not.
No,
indium?
it's not indium. Indium. No, it's not.
that looks like tech.
Look at this number. Look at the last number. That tells you how many electrons are in that 5p orbital.
Is it antimony?
The S.
All right, who got it first? Or who needs it more?
Me.
Who's me?
So Winifred.
I'm sorry?
Gee,
Winifred.
need it.
I didn't say anything, but you said who needed more. I said me.
Okay. Am I going to go with that? Is the other
You could-
person? Who's the other
Long as
person? that-
nobody opposes.
It was Kelsey, but I don't care.
It was
I don't-
who? It was who?
Kelsey, but I don't need it.
No.
Hold up, give me Kelsey's extra credit.
I
No.
needed more than all of y'all. Hold on. That's me.
Okay, guys.
So I
Another
have a
extra
question
credit. Another
Wait,
extra credit.
before you do it. Will you
Nope,
look
too
at
late.
the last number and letter? Like the
That's
last.
all you're doing.
Okay.
Which element is that?
Is it silicone?
Silicone.
Somebody answered first.
Silicone.
It was Kelsey again.
Who answered it second?
Emery.
Nah, we're going to go 9. I'll throw another. You don't get 2 extra credit points, but
Is
First-
it silver?
who's that?
Maria?
Maria.
Is it gold?
Nope, it is silver.
Yay.
I was one below.
Nope, I'm sorry. Wrong. I was wrong.
Is it
Richard, it was gold.
Yeah, what's up, Mr. P?
Dang.
Sorry. Richard, your last name.
Mondello.
That is your third, Richard.
Nice.
Okay, guys. Is this making sense to you? Because I have 15
Yes.
minutes to go over orbitals.
I understand that it's the last number, but once you get to the periodic table of elements, you have to have that label thing that you had pulled up.
No,
the
all you
chart.
got to do You can label it yourself. You're talking
Right.
about this
That,
slide, correct?
yeah.
All you
Yes.
got to do, just number the rows, 1, 2, 3, 4, 5, 6.
Oh,
And you have to realize that if you're going over to the D's, that's going to be 1 less than the S. If you're going over the F's, that's 2 less than the S. P's are going to
Okay.
be the same level as the S's are.
cool, cool.
All right.
Yes.
I have a lot of extra homework regarding this. All right. Okay. That is electron configuration. It's one way to diagram the electrons. We have a more specific way called an orbital diagram. And an orbital diagram is designated either with a line for each suborbital or with a box. Just like that. If I have hydrogen and I'm drawing the orbital diagram, there's only one in there. It is the 1s, only one electron. It gets put in with an arrow going up. Now, when we're putting electrons in, we have to realize some rules. Each orbital has its own energy level. The degenerative suborbitals, like the 3p's, the 3 suborbitals in 3p, all of them have the same energy level. And we got to follow Hund's rule. It is more energetically stable if electrons are placed one at a time in each suborbital with the same spin. In other words, when we're putting the electrons in the suborbital, if it's in the p orbital and there are 3 electrons, I'm going to put 1 electron into each one of those sublevels, and I'm going to designate it with an arrow going up. Now,
I have a quick question.
go ahead.
So when you're doing that, is there like, let's say you have something long like lead, will you have to do every single one? Or
Yep.
is there a way okay.
Now, when you are filling these in, because I don't want you trying to come up with unique ways, the easiest way to designate an electron with an up spin and one with a down spin, use your keyboard. Shift 6 or caret will designate an electron with an up spin or clockwise designation. A small v will designate one with a downward designation. So if I'm filling in an orbital, it gets filled in like this. I prefer that you do this up and down as opposed to side to side. Now, the 2p has 1s has 1 suborbital. First electron goes in up, second one goes down. The 2s, one goes up, one goes down. The 2p, we have it go in, up, 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 then down, down, down. 3s, 1 suborbital, one goes up, one goes down. 3p, again, they get put in, one up, one up, one up. 4th one goes into the first suborbital down. 5th one goes into the goes into the second suborbital down. The sixth one goes into the sixth one down. 4s, one up, one down. I'm going to go to the 3D. Five sublevels. So up, 1, 2, 3, up, 1, 2, 3, up, 1, 2, 3, up, 1, 2, 3. So if I have a sixth electron that goes in the 3D, it's going to go back and pair up with the first. A seventh would pair up with the second sublevel. Third would go in the third sublevel. Fourth would go in the fourth. Fifth would go in the fifth. Does this seem to make sense, ladies and gentlemen?
I have a question
Yes.
about the spaces between the suborbitals.
All I need you to do is just designate that they're separate levels.
Okay.
It doesn't have to be 3. You can do 4. You can do 5. I don't care
Thanks.
about that. Somebody else had another question. Female voice? Angelica,
voice.
perhaps?
Oh, I just said yes, like I understood.
Okay. Now, if I'm doing helium, I have 2 electrons going into helium. 1 orbital. In the 1s, it can hold 2 electrons. One goes in up, one goes in down. Now we're going to get a little fancy because these people actually have arrows. Lithium, I have now 3 electrons. My 1s is filled. So that extra electron goes in the next energy level orbital, which is the 2s.
Each one,
What's that?
one can only hold 2, right?
Each one of these lines, each one of these suborbitals can hold only 2.
All right.
Beryllium has 4 electrons. First one goes in up on the 1s, second one down. The third electron goes up into 2s, the second one down. Boron, 5 electrons, 1 up, 1 down. Next level, 1 up, 1 down. Now, legitimately speaking, it doesn't have to go into the 2px. It could just as easily go into 2py or the 2pz because these energy levels are all the same. Now, can somebody tell me carbon has 6 electrons in it? Where is that next electron going to go? I have 3 choices. I can put it in the next suborbital with the same type of spin as the first one. I can put them both in the first sublevel, one going up, one going down. Or I can put them in 2 different sublevels, one going up, one going down. Go ahead, Noah.
I believe it was option 1.
Remember how you fill these sublevels. Each sublevel gets filled before we pair them up into one sublevel. So that means this one is down, can't be used. The second priority is when they get filled in, they all have the same spin. So they get designated up. So nitrogen, how does nitrogen's? How does nitrogen's next electron go in? Nitrogen has 7 electrons. How does that 7th electron get put into this orbital diagram?
Up.
Would it be down? I don't know.
Remember, I have to fill all the sublevels before I can put a second one, before I can pair electrons into one sublevel.
It's gotta
So
go
first
up.
of all, which one is
Okay.
it going to go into?
We're going
The
to go.
last one.
It's going to go into the last one. Now, what type of spin? Is the arrow going to go up or is the arrow going to go down?
Up.
Up. It's going to look like you see right there. Oxygen has another electron, it has 8. I have already filled all my sublevels. I have to pair it at this point. But when I pair it, it has to go in to that sublevel with the opposite spin. So the next electron is going to go back into the first sublevel, down this time. Fluorine, again, I have to pair it with another electron, but when I pair it, it has to have the opposite spin. Neon, opposite spin.
So pretty much the order it's gonna be is up, down, up, down.
Not, well, no, Richard, it's going to be up, up, up.
Yeah, you're gonna fill all the first ones with up, and then you're gonna go back through it and then fill them up with the downs,
Correct. Absolutely. That's the pattern you're using.
depending on the amount of electrons.
Correct.
Okay.
If I was doing it with the d electrons, say I had 3d6 like iron, I would fill each one of the 5 sublevels with one arrow going up. Then that 6th arrow would be in the first sublevel going down. Is there anybody that's confused with this?
Nah, it makes sense.
Follow the mantra. I told you at the very beginning, follow my mantra. If you follow this, you're going to do well on these. I found that most of my intro chem students love this. They love quantum mechanics because it has a repetitious pattern to it. Okay, I got 3 minutes left. And I've got examples. Guys, write the electron configuration for calcium. From now on, and I probably will go over, guys. From now on, I am going to just be doing sample problems with electron configuration and orbital diagrams. So if you care to take off, that's fine. Once again, I really wanted to tell you all, it really, really has been my honor teaching you guys. It's been fun. You guys made it fun. I've had classes where I have to drag them through this kicking and screaming, but you guys have had fun with me, and that made it all the more enjoyable. I really did look forward to 12:30 each Monday and Wednesday. I really wish you all the best of luck. So guys, if you want to cut out for me now, go for it. I need to have you write the electron configuration for calcium, which has 20 electrons in it.
Do we tell you?
I think I'm going to show you in a second.
Okay.
I'm actually waiting. It shouldn't take you longer than a minute to do this. So I've been waiting a minute or so. Maria, how long did it take you?
I mean, since I already had lead written down, I already knew, like,
Okay.
I had.
Did you have something that looked like that?
Yes.
Are we good, guys?
Yeah.
Alternatively, up to this point, up to the 3p6, that is argon. So I could abbreviate it as argon in brackets for S2. Okay, 1 second. Ah, crap. I want you to write the electron configuration for bromine. And by the way, we are over time now. Are we good, guys? Does this look like what you have?
Yes.
Okay, I'm ending show right now because I want to get into hopefully some orbital diagrams. Which element is this?
Cobalt?
Cobalt? Yeah.
All right, guys, if you get hit with something like this and you want to check up on yourself, just count the electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 24, 25, 26, 27, 27 electrons. We're at atomic number 27, cobalt. If you want to check yourself. Now, how many unpaired electrons does cobalt have in its ground state?
3.
3. Did you see how she got that, ladies and gentlemen?
Yeah, she looked at the carrots. Right?
Yep, she looked at the
Right.
carrots. Okay. Good. You can't see it. What is this element?
Argon?
4.
Oh, wait.
You're right. Absolutely. It is argon. Now, it also is something else. It also is vanadium plus 5. Because if you look at vanadium has 3 3d electrons. It has 2 4s electrons. So if vanadium loses 5 electrons, it will have the same electron configuration as argon.
Where is vanadium?
3d 3 over. Between,
3.
yeah, just to the left of chromium.
Oh. Wow, I feel like I haven't seen that one. Yeah, I see it now.
How about this one? Last one was right. You had argon. What is this one?
Potassium?
Potassium. All you have to do, if I'm asking you what element this is, all you got to look at is the energy level that is the highest. This has 1 electron in the 4s. If you count down 4 rows, that is the level of potassium or calcium are the possibilities. There's only 1 electron in there, so it is potassium. How about this one?
Chromium.
And that was my last example. Are you okay with electron configurations?
Yes, sir.
Yes.
Is this stuff kind of making sense?
Yeah.
I would strongly suggest where is it at? Trying to find. Nope, that's not it. Maybe it is it. It is it. Okay, ladies and gentlemen, I would strongly suggest that you do two sources. One of which is, if you look down here under the tests, there is a practice test 4 with an answer key to it. That will give you some practice doing these problems. The other place is, if you look in, the last homework assignment you had was with Vesper and with Lewis dot structures. So if you go into homework May 5th, 4th, you have a couple of things here. Electron configuration with answers, and it's going to give you longhand, shorthand configurations, which elements are there, and it gives you the answers.
So is our entire test basically on this?
Nope, your entire test is going to consist of gas laws,
No, okay.
Vesper, Lewis dot, and the math problems we did on Monday and the stuff we did today.
Okay.
That's all I got, guys.
All right, Mr.
Oh,
P.
yeah, we needed.
Thank you.
Take care, guys. I've
Yeah.
put some dates for homework. I believe it is the Saturday before the final. You have up until then to complete the homework assignments, albeit at a penalty. But remember, even if you do the homework, quantity is going to count for half of the homework grade. So it's going to help you double.
Is
Guys, if you have nothing else,
there any extra credit we could do? What if I watch?
there will be an extra credit question after the 4th test. There will not be one for the final. Unless I decide to put one in at the last second.
All right.
The final open notes.
Yep. Everything is open notes. Let's fit. Come on.
Yeah, I like that. That's cool.
Well, first of all, I allow, normally when I'm in a face-to-face class, I allow you to have one sheet front and back of notes. Now that's just me because I believe that I don't want you memorizing things. I'd rather have you implement information than memorize, because memorization, as somebody once said, is a useless tool. So that's one thing. The second thing, how am I going to prevent you from looking at this stuff anyway? Realistically, if you guys want to look at stuff, you're gonna. The only thing I can do is I can have the proctor look and make sure that you're not using another browser to look up answers. That's all I don't want you to do.
How do you got a tattoo of the formulas on my arm?
Richard, I'm surprised you haven't done it already.
Dang.
Have a
Guys,
good day.
you have a good day, guys. It's been a pleasure.
Thanks, Mr. P.
Bye.
You take care and good luck to you in whatever you decide to do.
Thank you.
I'll see you in the fall.
Thank you, Professor.
Hopefully,
Enjoy your summer.
I will. I'll be in Montana in the summer.
Oh, that sounds like a good time.
Glacier National Park. Gonna take a train riding from Denver to Salt Lake City. And hopefully it's not gonna be cloudy.
Mr. P, have a good one. Enjoy your trip.
Take care.
So we don't have any more lectures? This is
That's
the
it. Ian, this was it.
all right. Well, I hope see you around.
I hope to see you around. And
Thank
take
you.
me in the fall. If you're taking
will.
Chem 1 in the fall, take me in the fall. I'd be glad to have you.
Thank you. I will.
Are you
Have a good one.
again in the fall?
I'm sorry, Winifred.
Kim 1.
I'm teaching Chem 1 lab in the fall, face to face on Fridays. Generally speaking, that is the most fun class I generally have because Chem 1 students generally know what they're doing and nobody's there to bother us. So it's really the favorite class I have of the semester.
Mr.
Not
P,
that you guys aren't fun.
No shade. It's okay.
Okay, guys.
All right.
Take
Mr.
care.
Everybody.
Good luck to you. If I see you around, keep the number. Keep the phone number. It's good for ever,
Thank you.
at least until I move from South Florida.
All right.
Take care.
Take care. Bye-bye.
Bye.